Hello and welcome to EP2P04 topic number 4. This is going to be trusses, machines, and distributed loads. So last week we covered static equilibrium of extended objects in 3D subject to applied forces and moments. This week we're going to introduce simplifications to this analysis in 2D that make it easier to handle and understand larger problems quickly, especially problems that require analyzing many connected objects that form a superstructure. We'll also look for simplifications for two force members and how to analyze structures made up of them, which are called trusses, define and analyze simple machines, and learn how to analyze problems with distributed loads. There's 6 different ILOs intended learning outcomes for this week. 1, you can use the force component method to quickly analyze 2D static equilibrium problems with many interconnected frames. 2, you can recognize two force members, show how they lead to pure tension or compression reactions, and use this method to simplify solving static equilibrium problems. 3, you can recognize and explain zero force members. 4, can solve pure truss problems with the method of joints or method of sections, understand why these work, and apply their lessons to better understand and solve frame problems. 5, can analyze simple machines, and 6, can analyze problems with distributed loads. Okay, 2D static equilibrium simplifications. We solved this problem last week. We had this beam that's fixed into a wall here, and we're applying 3 forces on it and a moment at one spot. And everything is just in 2 dimensions, right? All of the forces are only in x and y. The moment is purely in z, and everything is applied at a location in the xy plane at z is equal to 0. In this problem, we set it up with still the full vector equations. We just said the net force is 0. The net vector force is the 0 vector, and the net torque on this is also the 0 vector. But since all of the forces are in the xy plane, we definitely don't need to do too much work to solve the z equation. It's just a trivial equation. It says 0 equals 0 because we don't have anything added here in z. None of the forces create anything in z. So this just said the z reaction force is equal to 0. And for the torque equations as well, we didn't have any action except in z. So now the x and y torque are always, for this type of problem, the x and y torque equations are also trivial because none of these forces produce any torque in the x or y direction about any point that's in the xy plane. So why is that? Well, let's check. Suppose we take some arbitrary moment arm r, and we're going to be crossing that with a force which is only in x and y, right? We've got no z component. Okay, so this force, when we take the moment arm and cross it with this force, we're going to get a torque, which we can model like this. Let's just call this Rx, Ry, and Rz, Fx, Fy, and 0. Okay, so let's check here. We have that the torque vector has an x component of torque, which is given by negative Rz Fy, a y component of torque, which is given by Rz Fx, and a z component of torque, which is given by Rx Fy minus Ry Fx. Okay, so if we don't have any z component of the force, then the only way we can get non-z components of the torque are if the moment arm has some z component, which is to say that we're going to be finding out the torque that these things produce about some point that's displaced from these points in the z-axis. But if we're only ever finding the torque about a point in the xy plane as well that's not displaced in z from these forces, then the Rz that we use for our moment arm is also going to be 0. So by just choosing a torque location that's in this plane as well, that's on this object in 2D, we also don't have any torque about x or about y. So that means that we can similarly just have trivial torque equations in x and y by choosing a spot that is in the xy plane. So we're left with only 3 useful equations, right? The only useful equations we have when solving this then are that the net force in x is equal to 0, the net force in y is equal to 0, and the net torque about Z is equal to 0. So then, what we can say is that for every force applied about every point in the xy plane, we'll find that the torque in each of those directions is equal to 0. Yeah, so another way to put it is as described in this sentence here. When you have a force here and you have a moment arm here, they're only going to produce together a torque that's in plus or minus z exactly. It's not going to produce a torque that's in the x direction or the y direction. We have two vectors that are in the xy plane then, moment arm and the force. So when you cross them, you're going to get a vector that is perpendicular to the xy plane, and that's plus or minus z. So those are the only vectors that we can get, and all of the action is happening in the z direction for torque and in the x and y directions for force. So let's set up the problem with that in mind. This means on the diagram we can lay out what the forces are, so you don't have to look back at what they were here and lose that information. I've gone and copied them into the diagram there. We know that since all of these things are going to produce only torques in z, then we're only going to need a z moment to respond to them, and we're only going to need x and y forces to respond to them at the wall. So the wall's reaction is going to be entirely captured by two force components in x and y, and one torque component in purely z, one moment in z. Okay, so by the way to solve this in faster form without having to worry about vectors so much then is to assign directions in component form. So break everything up into x and y components. We've written these as their components to start with, so this is going to be pretty easy to lay out the equations for. And we've got our x and y components assigned for the reaction and our z component for moment assigned there. So the directions we assigned are arbitrary. They might end up being negative, but if they end up being negative, don't go back and switch them. This is the same thing when you're solving circuits. You just assign a direction and what the value is in that direction. So we're going to say the wall is reacting with FWY down. If it turns out FWY is negative, no problem. That means it's actually putting a force up, but don't go back and redo your diagram or redefine this, because it's going to just make a mess of everything. So leave it as, just pick a direction. It's not so important. And then you might get positive or negative, no problem. So the vector of the force that the wall is reacting with would be negative FWX and negative FWY. And the vector of moment that it's reacting with would be 0, 0, negative MW, what we just called here MW. Why negative? Because the positive direction for Z is out of the page, and using the right-hand rule, positive torque in Z would be this direction, counterclockwise. So we've assigned it in the clockwise direction, which means it's in negative Z. Okay. So let's go ahead and write out the equations for this. We can start off with this sort of a setup and then just start typing out our x equation. So we've got in the x direction a force to the left of negative FWX. Then this, let's just go 1, 2, 3, plus 2 for F1, plus 0, and plus 3 for F3. That's the first equation. Then F in the y direction, the force in the y direction, we've got negative FWY, and then plus 2. This one is plus 3, and this one is minus 3. And for the moment, we've got negative MW. So let's sum the moments in the counterclockwise direction. So we've got negative MW, we've got minus 0.8. Yeah, yes, this is a almost misleading diagram here. We're saying M2 is minus 0.8 Newton meters K, right? So it's not saying that it's a scalar M2 that's minus 0.8 in the direction it's showing. It's saying that there's a vector which is minus 0.8 Newton meters K, and that vector points in the clockwise direction because it goes in the negative. It's that much minus 0.8 Newton meters in the K direction, or 0.8 Newton meters in the minus K direction, which is this direction here. Yeah, so that's why we're going to be subtracting it, because we are adding things in the positive Z direction, K hat direction, which would be out of the page, or counterclockwise. So we have a clockwise one, that's why we subtracted, and then we got another clockwise one, that's subtracted, and then we've got the torque created by, I guess we have to decide, now it didn't matter for the moments, but for the forces, we should decide where it is that we're going to find the torque about. How about the origin? Sure. So about the origin, we've got two components from F1. We've got its y component displaced by this point x, which would be plus 0.48 in x times the 2 newtons in y. And then we've got its x component. That's going to be twisting it this way, right? So minus the 0.04 moment arm times the 2 newtons for its x component of force. That part is twisting the thing this way about the origin. What about F2? It's going just up, so we have only the 0.3 over to the right and then the 3 up. So that is the positive direction, counterclockwise. So plus 0.3 meters displaced to the right times 3 newtons up. That's the torque created by that one. And then, let's see, F3, we've got over to the right, and its y component would be minus 3. So that one's going to create one in the clockwise direction, which is negative. So that's minus 0.32 times 3 newtons. We've incorporated the amount that it's, the fact that the 3 is down by saying 3 and then that much and put the minus in front there. Okay, so let's just double check. Positive defined as counterclockwise and negative defined as clockwise. So MW clockwise, torque about the origin. M2 clockwise, moments create the same torque about every point. Then we've got plus 0.48 times 2. That was this one over and 2 newtons up. And then we've got minus 0.04 times 2, which is up, and then this. So that would be one that is in the minus direction, clockwise direction, okay? And then plus 0.3 over and 3 up, yep. And then we've got minus 0.32 over and 3 down. That's where the minus came from. So that one is clockwise as well. Okay, so this should give us the same results for the force and moment as we found before. So let's check. We've got 2, 5, and positive 0.02 for the moment in these directions. So here's our notes from last time, and it doesn't match the moment that we found when we set the force about the center, but it does match the moment that we found when we set the force about the bottom. So the force and moment components were the same as if we were to set the force about the bottom in this problem. And the reason for that is because we found the torque about the bottom and neglected any contribution from the wall's reaction, which is only valid to do if the wall's reaction happens to also be placed at the bottom of the connection there. Now we actually drew it in the middle there, so probably we should go and correct this and say that, yeah, okay, we're also going to have some torque contribution from the wall, not from FWY, but from FWX at 0.05 up. So let's see, 0.05 up and FWX, that together, that cross that is going to create a torque out of the page. So that's a positive one. So that means we would need to add to this plus FWX times 0.05, and that should give us the same result we had last time for when we set this about the middle. Let's check. Yes. So 0.27 in the direction we drew MW at, which is into the page, and that's why it ends up being the same as our negative 0.27 Z component for the vector moment the wall produces. So right now you might be thinking, all right, well, that's all well and good, but no thanks, Dr. Minnick, I'm good. I like this full vector thing that we did last week even better. That's great. I like the theory enthusiasm that you're showing for doing the full vector form. This method that we're doing this week is a lot more popular in engineering if you're solving the problem quite a lot. Doing this 2D analysis is a good thing to do in order to get a better understanding of where these where these forces and moments come from and what makes them point in one direction versus another. So at the start of the problem, we can kind of see everything's going to the right, so we expect it to be a positive reaction to the left in x, and everything's going more up than down, so we expect this one to be positive. And then guessing what they would do for spinning this makes it kind of in that direction. So this would be the positive direction to guess for that. But it's especially good when we combine this method next week with our ability to analyze internal forces and moments. So this is going to pay dividends. Understanding how to do it this way is going to help a lot when we make things much more complicated soon. Now, the other part is that it's also quite useful for analyzing machines, and especially for analyzing trusses and things with distributed loads. And where it's really shining is when you don't have to worry about this complication from the beam thickness. So if the beam is relatively thin in the y direction here compared to the length direction, so that we don't have to worry about this displacement up and down, where we're putting the force here, and then it lets us solve the problem with a much simpler setup. Well, let's do one of those problems with thin beams. Here is a setup, and let's imagine the beams are actually quite thin, and we can ignore the width of the members when we're considering the coordinates of the points. Like the pins are small compared to the members, and we're giving exactly the coordinates of where the pins are in the center of the bottom. We don't have to worry about this width and whether we're applying it at the center or the side or something for the reaction force there. Okay, and our goal is to figure out what the reactions are at all the pins and at the fixed support A. Okay, and they tell us what the mass is, 1 kilonewton. Okay, so a mass of 1 kilonewton, a weight of 1 kilonewton, weight in force. Yeah, mass would be about 100 kilograms if we're on Earth here, because G is 10, or pi squared, depending on whether you're in grad school. So what we have here for this is a setup that we're going to solve using the component method. So the first step is to copy this and open up our paint.net and paste it in there. Now, what we're going to do is split up, because we want to find the reactions at these different parts, split up the thing into different sections. So first, let's get maybe this thing and put it over here, and then we'll get, how about, circle select, I don't want that. This one, box select. Okay, we'll get this thing, and we'll put it over here, and then we'll get this thing, and put it over here. Yeah, great. Now we can draw some vectors. So let's get some colors going on, maybe red, sure. And let's, that's a little bit small. Maybe we'll go for size 4, sure. And then hit / to add an arrowhead. And yeah, that can be the reaction, why not? And then we've got some horizontal components and horizontal components there. Make those about the same, and horizontal components there. And now let's go with a different color for the vertical components, just so that we can draw them differently. The important part is if I draw this one up, I've got to draw this one down, because those are Newton's third law action-reaction pairs, right? This is also point B, although I seem to have cut off the B label at this point. Let's put that B back in. Okay. Yeah, that looks pretty good. Okay, seamless. Next, we'll go back to our color for these arrows. Draw one vertical there, vertical component there, that and that. Again, Newton's third law action-reaction pairs. You have to make them assigned in the opposite direction. It doesn't matter whether we chose this one to be down or up, as long as we chose this to be the opposite. Because what we want to do now is label this. So let's go to times, make it look all equation-y, and put in italic stuff, and we'll call this CY. Then this is CY as well. And this would be DY, DY, BY, and BY. And then we've also got the horizontal components, which are DX, dx, cx, cx, and then joint B, bx there, okay? And reaction at A, we've got AX, and we had more room, so we just made the vertical one also the same color, but we do need to make a different color for the moment. Maybe we can use blue for that. There's the O, okay? And yeah, sure, that way. And we'll call this MA. Okay. So here's our free body diagrams, and this is useful because now we can go and write the equations for every one of these different parts and solve for them all. The other thing that we need to draw in is this external force. And the external force is there, not italic, 1 kilonewton down. Okay. Yeah, we can, this is it. This is okay for free body diagrams, but we can do even better if we note what the locations are of things, right? If we note the relative dimensions on this diagram as well. So what do we need for that? The only important dimension for this part is the vertical distance. And let's get rid of our arrowheads there, and we'll label what these locations are. Okay, so this is the 0, 0 location from A. This is 2 meters up, and this is another 2 meters up at 4 meters. So maybe we'll call this 0 meters, 2 meters, and 4 meters. Okay, and then over here, we care about the horizontal distance, horizontal displacement. We can make this a little bit smaller maybe if it's kind of interrupting the other diagrams, maybe size 2, and then we can change this one with the period to make it a little bit more transparent, and then say that this is 0 meters and 2 meters over to the right. And then this one here is also at the same 2 meters. Maybe we'll just label points for this. This is point 22, and this is point 0.04. Great, in meters. All right, so now we've got all the information on the free body diagram. We can select everything, copy it in, and then say first, draw a free body diagram and label all of the force components, force and moment components. Okay, and there we go. Now we can generate the equations for each frame, each of these components of the problem, by declaring that each is in static equilibrium and therefore has no force in X, no force in Y, and no torque about Z. Let's say no torque in Z about any point. So this will give us 3 equations in, in the number of unknowns depending on which thing we're talking about. But because we've linked them up together, we've used the fact that up here at the top, through the joint, we are transmitting force to from one frame to the other. Then we know that the same force in X that this frame is putting on this one at joint C is the one that this frame is putting on this one at point C. That's transmitted through the pin. If you like, you could think of the pin itself as being in equilibrium, and it is. That's kind of like an implied thing that we had. So we could have drawn just pin C, if you want to see how that works, and started off by saying, All right, well, we've got a bunch of forces on this. We've got what's pulling on pin C? Well, there's this frame over here to the right, and it is putting some horizontal force and some vertical force. Right, we're not really sure what that is. Let's call that maybe force on C from maybe force of CD on C in the X direction, and this is force of CD on C in the Y direction. It can only produce a force. We can't produce a moment because it's a pin. It's a frictionless pin. It will just spin instead. And everything's just in the XY plane, so it only produces two force components. Then we also have the force of ABC on pin C. And let's just arbitrarily say that the X component of that goes to the left, force ABC on C in the X direction. Labels are kind of long, but anyway. And then we've also got a Y component to that, arbitrarily assigning it down, force ABC on C in the Y direction. Now, maybe you can right away solve for what has to be true about this. For the net force in Y to be 0, we need that those two forces on pin C cancel. So because C is only connecting this frame to this frame, you immediately can tell that the force that ABC is putting on pin C has to be canceling the force that CD is putting on pin C. So that means FABC in the X direction has to be the same strength but opposite direction as FCDC, and force of CD on C in the X direction. So the way we've drawn it here, this is the same as that, and this one's the same as that. And that's how you are able to translate it. Oh yes, okay, we've just got at joint C, a force CX in the X direction on CD, which is equal and opposite to the force CX on ABC in also in the X direction. Yeah, so this is the same as that, but they point in opposite directions. Transmitted through pin C, because pin C can only supply forces to the things it's connected to and not moments, and because there's only two things connected there. If there were three things connected at the same pin, it gets more complicated, and we'd have to, in general, draw a free body diagram for the pin as well and kind of work that out. Its equilibrium condition would not be sort of trivial so that you can skip it. Okay, so let's get going then. This thing, we've got again, restart, solve, and let's start writing out these equations. So on ABC, we have a force in the X direction, which is AX plus BX plus CX, and that's it. Now we've got forces in the Y direction too. We've got negative AY plus BY plus CY, and that's it. And we've got some torque equation. We can take the torque about any point we like. Let's take it about A to eliminate these two unknowns. So about point A, the Y components, BY and CY, don't produce any torque, but the X components do. We've got MA assigned in the positive direction this time, so we'll say MA, but this creates a negative one. So minus 2 times BX minus 4 times CX. Yeah, so 4 up and CX over to the right. Okay, what about this one? Well, force in the X direction on BD, we would have minus BX plus DX. In the Y direction, minus BY minus 1E3, that's the 1K force, plus DY. And then we've got a torque equation, which would be DY. Let's find the torque about B. I like to think about on the left side. I find it easier to visualize. You do you, though. You do your style, right? So about this point, we've got one that's in the negative direction. That's clockwise. For 1 kilonewton, that's 1 away. I didn't label that in, but it's halfway there. It's 1 away. So we've got minus 1 times 1E3. And you know what? Now that 1E3 is showing up twice, I have a mental thing where as soon as I had to write a magic number more than once, it means I should probably have a variable. So let's say that W is 1E3, and let's put in W there. That's just kind of good coding practice. If you have to put in something more than once, then think, okay, that should be maybe a variable. 1 times W, that's the torque from that. And then we don't have a torque from DX because that's just in the x direction doesn't twist this thing about that point, but 2 away, dy will create a torque in the opposite direction that this is about point B, then the weight. The weight spins it this way, dy spins it that way. So we're good. Okay, next, this one. We've got, where does some of well, let's first do the force. Okay, so we have minus cx minus dx. Okay, so one of them has to be negative the way we've set this up here. Yeah, and then same with the y, minus cy minus dy. And finally, we've got the torque equation. So okay, hey, look at this. Cx and dx have to be equal and opposite, and dx and cx have to be equal and opposite too. That's interesting. And then what about the torque? Torque about point C. Well, you can sort of take the torque about any point. Probably easiest, actually, to take the torque about this point here where they intersect, because then we have just a simple thing to like one moment arm cx there and one moment arm dy. So that torque equation says 2 up times cx is equal to 2 over times dy, or in other words, minus 2 times dy, making it spin in the other direction. And that should be it. We've got results. Okay, so dy is 500. Okay, let's see, does that make sense? We're going to need by to be negative 500 then, right? Yeah, so we're holding up this thing. And if by is negative 500, so it's actually 500 down, what about cy? Well, if dy is 500, cy has to be negative 500, pulling up. And that means this is pulling down and this is pulling down together with 1,000. Interesting. That's how this is transmitted over to there. So we need ay to be negative 1,000 then. Aha, looks good. What about the moment? The only thing that's producing moment externally is this weight. And that's 1 over and 1,000 down. So we expect the moment to have to be 1,000. Yeah, counteracting that. Okay, there's a check. It's actually really, this problem is actually really easy to just solve for the reactions at A immediately by looking at it and saying, oh, it's 1 over and 1,000 down. There's the moment. AX should be 0 because there's nothing else applied externally in the X direction. Yep. And AY is 1,000 up, or as we've assigned it, AY will be negative 1,000. But doing this whole thing out lets us get a check that what we got at A is correct, and lets us solve for all of the joint reactions in one go. All right, I've copied in the code and added in a little bit of an explanation there. Now let's explore some of this stuff in a little bit more detail. You might have noticed some weird stuff going on with CD here, or maybe even some interesting stuff going on with the pin. The pin, just by its setup, all applied at one point. We needed the force here to be equal and opposite to the force there. Yes. Now, what if we were to extend where one force is applied compared to the other, kind of like what's going on here? For the same reason that we needed these two forces to be equal and opposite on the pin, this frame CD only has 2 forces on it. So for the net force to be 0, the total force applied by C, the vector force, and the vector force applied by D have to be equal and opposite, right? When I say it has 2 forces on it, I mean it has the force that pin C is putting on it and the force that pin D is putting on it. Those are the only 2 things actually attached to this frame. Now those pins can only produce forces, right, and not moments. So not only do the forces have to be equal and opposite, like this, they can't be just arbitrary. You know, if one is down, the other one has to be up like that. But the problem is this creates a couple. So this is going to spin and not be in static equilibrium. It won't have no net torque on it unless the forces are not just equal and opposite, but collinear. The only time these 2 equal and opposite forces can produce no torque without being 0 is if they're collinear. So that is, they either point directly away from the other one's application point or directly towards. They could be negative and this would still work. Directly away points out like, hey, wait a minute, this member here, this 2 force member, so-called because it only has 2 forces applied on it at pins, and in other words, no moments applied on it, just 2 pure forces applied on it. For it to be in equilibrium, it's just like a cable. right? It's just like it has a tension. This force is the same as that, and you can treat it just like that. The only difference is these could be negative, and it's not going to fall apart or buckle unless they're too large. So it's like a cable that can have a negative tension. You call that a compression. Note that it doesn't matter if the beam is actually in the path between the two pins. I mean, it matters for structural integrity, but in terms of which way the force works, you could have this sort of squiggly line with a pin there and a pin there, and the forces would still point along the line between the pins, not on the direction the member necessarily goes, but just along the lines between the pins. Because why we needed them to point like that, again, was because to have no net force on it, they have to be equal and opposite, and to have no net torque on it when we can't apply moments from the pins, they have to be collinear. Well, that actually helps in a substantial way, because it means that a lot of the stuff that we did for CD in that last setup is already solved for us at the start of the problem, right? Rather than assigning things like this, we can say, you know what? At the start of this, we already know which way CD is going to point, at least to positive or negative. We don't need to guess those directions. We don't need to analyze it as a separate member. We can do a whole different setup where we pre-assign its direction. Let's look at what that looks like. So we'll take this same problem. We'll go make a new setup and just get lots of space for the canvas. Now we're not going to need to deal with CD because that's just a two-force member. It's a truss member. It's kind of in disguise, but yeah. So we'll take that thing, and we'll take that thing. And yeah. Okay. So what do we got? We got, do I want to use orange? Let's use red again. For sure. And we've got BX. Oops, caps lock. BX. And then we've got BY. Like that, and call this BY, and we've got force at A. Actually, you know what? I don't like BY being in the way of the wall there. Force at A, AY, and horizontally, AX, which is going to turn out to be 0. Okay, now for CD, it's just a force that's up and to the left, like that. Maybe we'll make that one orange, called CD. Tension in cable, it's not a cable, it's a truss member or a two-force member, CD, at a 45-degree angle. Okay, so up and to the left at 45 degrees, and then we can label this at 1, let's get rid of italic, 1 kilonewton. Yeah, now we just need the moment. This time it ends up being the other color. That's okay. Yeah, and we'll call that MA. Right. Sure. Now, if you remember the distances, then we can put those in too. This is 0, 0. This is 0.02, and this is 0.04. This one over here is 0.22. Okay, so here's the reanalysis of this as a two-force member, using the same new colors that we have before. There's a previous one from an earlier solution to that. I don't know which one you like better. Maybe this one is better because it's all purpley and has pretty much the same length for all of them. Maybe this one's better because it has more colors, has the points labeled without specifying they're in meters. So I mean, nobody's perfect, I suppose, or at least I'm not perfect. So the next thing we can do is label this out and try out these equations. Okay. So we'll again go W is equal to 1E3. That double restart there is kind of like save, do nothing, save again. That's common when coding. Yeah, we've all been there. Okay, so solve AX. Let's do the net force on this is equal to 0. AX plus BX plus CD. Now it's at a 45-degree angle, so we're going to have to take CD times cos of 45 degrees. But you may know that CD times cos 45 degrees, or cos 45 degrees, is 1 over root 2. Okay. Yeah, now in the y component, we're going to have negative AY minus BY minus CD over root 2. Now for the force about, not the force, the torque about point A, in the counterclockwise direction, we have MA minus BX times 2 minus 4 times CD, but only its x component. So again, over square root of 2. Man, 45 degrees is great. Makes all of these x and y components quite simple. Now we only have one more set of equations to get for this beam because we already dealt with the CD equation, the CD equations to find out from net force in x and y that the two forces have to be equal and opposite, and then net torque, they have to be collinear. So that's what gave those pieces of information. Yeah. So how much information have we determined if we've determined that one force has the same magnitude in x as the other one does? That's one piece of information. Same magnitude in y as the other one, but equal and opposite. That's one piece of information. And then the relative magnitude between x and y for the directions is the third piece of information. So that's where those three equations went to. It's figuring out that CD is, that the force of CD, member CD on pin D is equal and opposite to the force of ABC on, or rather that member CD on ABC, and that they're collinear. We know which way it goes already, which is what led us to this 1 over root 2 thing. Okay, we don't know how strong it is, the amount of the tension, but we know what way it points, at least to positive or negative. Like it might be in compression, this might be negative. It's not, because we worked out already that it is actually up and to the left there. But we know either it's this way or it's negative that way, meaning compression. We always draw it in tension and assign it like that so that we can remember that if it ends up being positive, then it was in tension, and if it ends up being negative, it was in compression. Okay. Yeah, so net force on this thing, finally, in x. We've got minus bx minus cd over square root 2. And then in y, we have by plus cd over square root 2 minus 1e3 minus the weight. And then the net torque about B, we've got minus 1 times weight plus 2 times CD over square root of 2. And let's see. So CD is 707. How does that compare to what we found before? Yeah, that is 500 times root 2. And that's what we got here, right? CX was 500 there, and dx was negative 500, so it was actually 500 over 500 up. Yeah. So 500, 500, square root 2. Yeah. So 707, same thing. Slight round off error there at the limit of where it's showing us the precision. Next, everything else looks the same too. So there we go. Using the two-force member analysis to immediately recognize the direction of the two forces on this two-force member have to be equal and opposite and collinear, you can pretend that instead of that frame thing that was there, this, because it's just connected with those two pins, it's as if there was a cable between those 2 points and analyze the problem that way. You can even build up entire structures where all of the frames in it are two-force members, all the members are two-force members, and everything is just applied at the pins then. So what you do then is analyze only the pins by itself. This kind of a superstructure, by the way, where all of the members in it are two-force members, is called a truss. So we have that here. Yeah, so if you maybe lay it up in triangles inside, then this sort of structure that you can build up this way can actually be quite stable while being incredibly lightweight, and has been historically very useful in engineering. So truss members are assumed to have negligible weight compared to the forces on them from the pins, and that's what allows them to be two-force members. As soon as the weight of the truss member itself is substantial, like this weight being applied in the center of mass or like distributed along the length of it, then you can no longer totally validate the assumptions that you made to say that all of the force on it is just from one pin and another pin, and then say that the forces are equal and opposite and collinear. If you have some other force applied in the interior, that ends up not being a two-force member, right? In this last problem, even though BC was also just attached with two pins, because it had this applied force externally on it, it was not true anymore that the force that this was applying was equal and opposite to this force. It was modified from that by the 1 kilonewton force, right? So if you don't have any of those forces along the structure, then this analysis is pretty good, and that's also going to work out well if the weight is small, or at least even if even if there is some force on this structure along the way, if it's small enough that it's not very big compared to the forces at the ends, then this analysis is going to work out quite well. So with the truss members, again, we can say that they're only in tension, which means that they've been pulled apart a little bit and they're trying to pull back together. We're kind of pulling on them like a cable, or they could be in compression, meaning the ends have been pushed together a little bit and they're trying to push back apart. That they've been compressed. They apply a negative force from what a rope would have applied. That's called compression. So in a past life, you may have dealt with trusses before. Here's a Physics 1 DO3 exam question. We've got this truss ABCD, and there's the 600 Newton force applied there, and figure out what the internal force is in member BD, and say whether it's compressive or tensile. Okay, so we could do this the same way as we'd analyze any sort of truss structure, which is to first split it up into a free body diagram there. And I just am noticing that I didn't draw all the forces on this thing. There's one missing. Can you spot it? It is the force between A and D. So we'll draw that thing in. Let's make this red to be consistent. There we go. And we'll call this AD. Yeah. Great. Okay. So that's pretty good. Maybe we're going to want to know the dimensions of things, like the locations, but it tells us that it is made of equilateral triangles. So we know what the angles are between, anyway. The angles are all going to be, this is a 60-degree angle, that's a 60-degree angle, that's a 60-degree angle. So the angles that these ones make from the horizontal are 60 degrees, and the angle it makes from the vertical is 30 degrees. So with that, we're in a position where we can go and analyze this. Let's give it a shot. So we'll put that one in to replace the one that I did earlier. And now we can draw we can write what the net force is on each of the pins. So let's go just pin by pin analysis, write the whole thing out. Solve on pin A. We're not going to have any torque equations because it's all applied just at that pin, right? We've got, hold on a sec. We're going to have coses and sines of 60 degrees. So maybe we should redefine these, right? C60 is the cos of what's 60 degrees in radians? Pi by 3. And S60 is sine of pi by 3. Cool. Now, maybe we can write this out a little bit more easily. On pin A, we've got AX, so minus AX, plus AB times C60 plus AD. You see how that works? We've projected AB onto the horizontal. And then in the y direction, we've got minus AY plus AB times sine 60. Now, what about, let's just go alphabetically. So for pin B, we've got minus AB times cos 60 plus BD times cos 60 plus BC. And in the y direction, we have minus AB times sine 60 minus BD times sine 60. Yeah. And then what about pin C? So for pin C, we've got minus BC minus CD times cos 60, and that's it in the x direction. In the y direction, we have minus CD times sine 60 and minus 600 newtons. For pin D, we've got minus A, in the x direction, we have minus AD minus BD times cos 60 and plus CD times cos 60. Then in the y direction, we have BD times sine 60 plus CD times sine 60 plus dy. All right, let's see what we got. Does it make sense? dy is 900 newtons. So that's 50% bigger than the 600 Newton force down there, which makes sense because the 600 Newton force down is 60% farther away in x. So to produce the same torque about point A, because these are the only external forces that can produce torque about point A's reaction forces can't do that because they're at A. So to produce the same torque, this has to be 50% more force if this one's 50% farther, which is why we get 900. Also, it is positive, like we said it needed to be, so that's a plus. The thing's not going to rotate in or around or something. It's going to hold still. What else? So this frame here, this truss, two-force member, has to be in compression, right? Because look at the y force, look at the y direction for this pin. The only way we can push it back up and cancel out this is if CD is negative, because that's the one that produces stuff in the y direction. So this has to actually be in compression, pushing it that way, which means BC has to be pulling it that way, meaning it's in tension. It's been pulled apart to pull that way. So CD has to be stronger than 600 because it's not directly in the same direction to oppose it. It's a little bit off, but not that much off. So CD is 400 root 3. Root 3 is more than 1.5, so this is going to be more than 600. Yeah, so there we go. So CD indeed negative and more than 600. That makes sense. So BC is positive, and a fair bit less because it only has to cancel the horizontal component of this thing. Then BD, okay, now we're getting into a bunch of different things that are a little bit more complicated. BD and AB have to be equal and opposite because of how they're interacting at B in the y direction. So let's, oh wait, does that make sense? Yeah, I think that makes sense. They have to be, well, equal and opposite magnitudes, equal and opposite sizes there, but that's because they're already pointing in opposite directions. They're going to be net opposing BC. So AB is going to be positive, BD is going to be negative, the same thing is what I'm saying. Let's see. Yeah, okay, positive this. Is BD negative the same thing? Yes. Okay, so all looks pretty legitimate. Seems good. So this method of analyzing a truss, where you just set up all the pin equations and set each pin in equilibrium, net force in x and y at each of the different pins to get your equations, is called the method of joints. The pins are really the joints of the truss, so that's why this is the method of joints. But another thing that we could have done, which is sometimes better, is called the method of sections. Now how this works is you say, you know what, okay, yeah, this whole thing is in equilibrium, so let's first solve for what AX and AY and dy is, the reactions at the supports. Then once we've done that, we can cut it anywhere and say, you know, actually, this side by itself has to be in equilibrium, and we can immediately solve one more equation that gets at the forces that we want. Now, since we've already figured out what D is, any section that we apply is going to have no unknowns except the ones that we add to it by where we sectioned it, the internal stuff. So this would be a way that we could immediately get another set of 3 equations. When you do a full extended object like this, you have the torque equation back. It just vanishes at a pin because there's no moments applied and all the forces are at the same point. So you don't have a torque equation at a pin, but we do still have the torque equation when we do like a full superstructure like this. So now we'd have 3 unknowns from the internal things that we split across there. But we'd have 3 equations. So 3 equations to then figure out what any one of these is that we like. That's method of sections. We can explore that in the next example here. So for this truss, it's simple enough that it doesn't really motivate it. But for something like this, wow, what do we have? We have HIJKL, I think, is that 12 different letters? I'm going to pause and count. Yes, and you can't prove that I paused and counted. So definitely L is the 12th letter. So that's so we have 12 different joints if we were to do the method of joints for this, and with 2 force equations for each, that would be 24 equations and 24 unknowns. Oh wow, did I count this wrong last time? Yeah, it looks like 12 joints for 24 equations in 24 unknowns. Yeah, so that would be quite a lot. Instead of that, we can use method of sections to solve it immediately. When I say solve, I mean find out the forces in the 2 force members that they ask us for. So if they asked you for everything, for all of the tension and compression forces in every single one of these 2 force members, these truss members connecting the pins, then you may as well just use method of joints. You may as well lay out all 24 equations and solve them. But if you just need some of them, in this case CD, DK, and KJ, then we can do an easier time by first finding the support reactions and then sectioning it. Let's go ahead and do that. So, method of section solution. Sure, lots of space. Okay, now, with the whole thing together, I'm going to draw some forces here. Let's call this AX, AY, and then this one over here, FY. Great. And now that we've gone and drawn that, I'll get rid of the old solution, assert the entire truss. So this is a solution, actually. This is a problem from the old Engineer 2P04, which I'm not sure if it might, depending on if you're watching this in the future, this course might be totally gone. But since, I don't know, the dawn of time at McMaster, we've had a statics course, Engineer 2P04, and this problem was written by the ancient, the historical engineer, Dr. Sivakumaran, maybe, and this is a problem from ancient history that some say you can still find in a custom courseware for Engineer 2P04 if you know where to look. So here it is. This is something from my version of 2P04, which by itself was eons ago at this point. So let's so I guess it's a little bit of a historic problem. How do we analyze it? Well, we first find the forces applied to this thing at the supports by doing 3 equations and 3 unknowns. And then what we're going to do is section it so that we can just get a simple setup and solve for what those forces at the support, what those forces just in this interior thing have to be. So this one will be CD. There's going to be DK down there, down that way, and KJ over like that. Yeah, so we know that they're going to be in those directions. They might end up being negative, but that's our strategy. Okay, so let's set it up. First step is to solve for ax, ay, and fy. And how are we going to do this? We're going to look at the whole structure as a single object and say that it's in equilibrium. And so that would be the forces in x are 0, and that's just ax, so that one's gone. And forces in y are 0. Ay plus fy minus 30k. Then we're going to have the net torque about A is equal to 0. We could have picked any point, but A is nice because it eliminates two forces, even though one of them we already know is 0. Okay, so let's see. About A, we have 2 meters over minus 15k. So that's going to be 2 times 15e3. And then we've got 2, 4, 6 over times 15e3. And we've got, that was 6, so this is 8 over plus 8 times fy. Yeah, so maybe you can see already that fy itself has to also be 15e3 because we've got minus 2 and then minus 6, 15e3, so together that's going to be minus 8. And that means so does ay. Yeah, so there we go, 15,000 all around, except for ax, which gets nothing. That's the first part. Now we can go inside and solve the net force and torque on this, on this part of it, just the right-hand section of it, because, you know, this thing as an object has ax, ay, and fy on it to hold it still and can't be moving. So the net external force on it would be those 3 plus those two 15k forces that are applied. But on this right-hand side, it only has one of the 15k forces, and it doesn't have ax and ay on it. Instead, from the right-hand section of it, it only has these two, but then it also has these 3 internal forces, cd, dk, and kj from those truss elements. So on that one, we can write 3 new equations. Net force in the x direction is 0, net force in the y direction is 0, net force in the z direction is 0. All right, so in the x direction, we've got minus kj minus cd times, well, what angle is this at? We've got 1 up, and we've got 1 over. Well, that's our 1 over root 2. Again, that's a 45-degree angle. Minus cd over square root 2. And then minus dk, because that's pointing to the left as well. And what's the x component of that? Well, it goes 1 over, and it goes 1, 2, 3 up. So that would be 1 over root 1 squared plus 3 squared. Yeah? So the way that you might think about this is that to get the horizontal component of it, we would multiply this by the cosine of that angle. So you could say, all right, this horizontal component is equal to the magnitude of this times the cos of this angle. Why? Because cos of this angle is equal to this force, dk, over the horizontal component, dkx. So let's maybe put it like this. dkx times cos of theta, or rather dkx is equal to dk times cos of that angle, right? But the cos of that angle is equal to adjacent over the hypotenuse, which would be 1 over the square root of 1 squared plus 3 squared. Aha. 1 over root 10. So there we go. That's how you might get the direction pretty quick for that sort of a setup. Okay. Yes. So did we get all the horizontal components on this? Just those 3. Yeah. What's next? We've got the vertical component. So that's fy minus 15e3. Those actually are going to cancel. Plus cd over root 2 minus dk. Now the vertical component would be 3 over root 10. Yeah. And now what about the torque? So we can pick any point we like for the torque. How about point D. Yeah, that sounds great because I'd rather eliminate those two from applying their torques about any other point. Everything else is nice and horizontal or vertical, so that's going to be a lot better. Let's try that, and then let's deliberately use a different point and see if we can get the same result. So about point D, we're going to have 1 over and 15k down. That's a clockwise, so that's negative, minus 1 times 15e3, and then 3 over and fy up, plus 3 times fy, and then we have 3 down times kj, that's clockwise as well, minus 3 times kj. So this should solve for those 3 fourth components. Let's just double check how this weirs. So they're all around the same order of magnitude as fy and ay, which kind of makes sense. You'd be weirded out if they were way off, like if they were all really small or all really big compared to those two forces, then something might have gone wrong here. Yeah, let's see. CD is negative, so it's pushing here. DK is negative as well, pushing there. So we're pushing to the right, and maybe this one's a little bit stronger. Hard to tell whether it's so up or down. Looks like it's mostly balanced. They actually have to cancel out completely because these two are just vertical and equal and opposite, and this one is totally horizontal. So both sort of pushing to the right, and then kj is pulling to the left, so that cancels that out. And now from a torque perspective, if they're pushing and this is pulling, that's going to cause it to spin this way, which cancels the spinning the other way that these two are doing. So at least from a quick sense check, it seems like it makes sense. Okay, let's try again. But this time, let's use a more complicated torque equation. So I did Control J to get an execution group after the current one, by the way. That's this thing. Control K would put one before, and I'm hitting Control Z to undo those. So this third thing, if we don't want to use that torque equation, we want to use a more complicated one. We could find the torque about point F. That'll be the hardest spot of the obvious spots there. Okay, so about point F, we have kj producing no torque. We have a positive torque from this 15k. So that's 2 times 15e3. 2 over this way, 15e3, positive torque. And then, let's see, CD's y component would produce a negative torque. Actually, you know what? I mean, this sort of looks like it's in line. So maybe CD produces no torque. Let's check. We've gone over how much? 3 over and 3 up? Right. So, and it continues over another 1 up and 1 over. So it's totally in line, meaning it produces no torque either. You know what? This spot actually wasn't so bad. It's just DK that's the problem, because we have to sort out what this, well, potentially what that angle is, or use components again. So DK, we will have that it is, let's see, it's over that much, and we'll take the y part of it. So that's a positive 1. So DK's y component was, so it's horizontal displaced by 3, and then the y component is times 3 over square root 3 times dk. And the x component would also be, is that right? Yeah, the x component would also be moving it in that direction, right? Because it's displaced up. So that would be plus also 3 up, and its x component is going to be dk times 1 over square root, sorry, I said root 3 earlier. This should have been over root 10. Yeah, this fraction, this has to be a fraction, right? Root 10 is larger than 3, and this is the part of dk, which is in the vertical. This is the component of dk, which is in the horizontal. Yeah. Okay, so we should get the same result if I have typed that out correctly, and we do. Good check to do a torque about a different spot whenever you have a tricky torque equation to make sure that you've got it right. One neat thing that shows up in these problems sometimes, another thing to look for, is a zero force member, and that's something like BL here. So this has to be a truss, but then look at what's going on at pin L. Right at pin L, you can see that AL and LK have to be totally to the, because they're totally in the horizontal direction, nothing can oppose BL there. So BL has to be 0 for this to be an equilibrium. If you can notice that, then you can simplify some stuff out right away. If it wasn't for this 15K force then, point BK would also be a zero force member, and that lets you sort of simplify things further. Sometimes these start kind of a chain reaction. Let's have a look at this one here. This is also so these two are both zero force members, right? Because there's nothing else applied at D. You can see that CD and DE, well, the only way that this thing can be in equilibrium, because they don't go in the same direction, is if those forces are both zero, right? Because if they're not both, if one of them is not zero, the other one has to be opposite sort of the direction, but then they're going to create a net force off to the side, right? So the only solution is that they're both zero, and these are both zero force members then as a result of this setup. So next up is another example of truss and frame members together. So let's just talk about it a little bit, and I'll leave it for you to solve. There's a solution down below if you'd like help. Give yourself a chance to go through it. There's two different solutions. There's sort of a deep dive, long explanation solution, and there's a fast mode solution that talks through it. Just a little bit of analysis at the start. Can you find the trusses and frames in this? Well, this is a 2 force member, but it's actually a 0 force member because of this connection at E, right? And this is a 2 force member, this is a 2 force member. This is not. This is a frame, yeah? Because it's got this external force on it. So when you look at joint F, you would call this EF just to the left. You know it's got to be to the left. But at pin C, we would have that analyzed as CX and CY. What about A? Well, this is a full, this is a fixed support, so it also can apply a moment. Yeah, so here would be the setup. If you can get to the free body diagrams, then you've got a lot of the thing set up. Good luck. This exact same analysis method that we've been doing also helps you analyze machines. A simple machine is just a mechanical device for transmitting forces. You use it to get some desired result, like a scale or maybe to amplify force. The analysis, though, is exactly the same as frames. So here is a setup that involves, well, I'll try and kind of talk you through what's going on here. This is a diagram which is a little bit hard to see, so why don't we spend time touching it up. Whoops, let's try again. New, Control-N, 1900, 1080, why not? Yeah, so what's going on in this diagram? Well, there are some frame elements and pin connections. So let's put in the pins, and we're going to use the paintbrush here and draw them in. There's a pin, and there's a pin. So this is a single frame element with a pin there. There's a pin there. Whoops, that one kind of missed. Let's go make this a bit easier. Pin. Yeah, and there's a pin there, and a pin there, and a pin there that this thing is connected to. Okay, so now that you can see how that thing works, this whole setup, this is not connected to this thing. This can move freely. We've got a 2 force member, a 2 force member there, and then this is a frame, and this is a frame, and this is a frame. Okay, so with this in mind, let's try and set up what's going on for the frames by drawing the frames kind of by themselves, right? So how do we analyze this? Well, we're going to start off with this same diagram. Let's actually kind of take this first thing here and say, here's where the pins are. Yes. And now let's analyze it by splitting into the frames. So to split it into these different frames that we've got, we have a few different parts of this. We're going to have just the top part there. We're going to have the middle part by itself there. And we're going to have the bottom part there. Let's grab H as well. Sure. Now why do this? Why split it apart like this? Because this is going to allow us to draw out the forces. So now that we've got this thing by itself here, we can label where these forces are in this thing. So here we've got FG. And then we've got this force here, which is ED, or maybe DE, I guess. Let's try and be alphabetical. DE. Same one up and down. And then we got a couple more. We've got this mass, and the problem tells us that this is a 50-gram mass. So this is, how many newtons is that? 50 grams. If G is about 10, then we've got 500 millinewtons, so 0.5 newtons. 0.5 newtons down. And what else do we have? We have this 10 kilogram thing, and this then is a 100 newton force there. Okay, so 100 newtons there, DE and FG at those spots, and 0.5 newtons there. So here's our diagrams. It's really kind of three different free body diagrams, making use of the distance written along the top there. So now that we've got this laid out like this, we can pretty quickly do some, get some solutions to this with a few torque equations. So torque about point C being 0 tells you that 75 times DE is equal to 300 times FG. You see that? So FG is 300 away, and DE is only 75 away. So that means that because DE is a lot closer, it has to be a lot more force than FG. What about about point B? This sort of shows where the first magnification of force shows up. We have FG times 100, which is kind of pulling this up, has to be equal to 100 plus 300 plus 75 plus 350 minus X times 0.5. And then we have one more torque equation here at the bottom, which says that 50 times 100 has to be equal to 375 times DE. Okay, and that tells you what X has to be. We also found the interior forces. So let's check. X has to be 150. If X is 158.3 millimeters, then this weight will balance out the 100 Newton weight of this I don't know, pile of gold nuggets here. Ah, yes. All right. Hold on. Very important thing to do. That didn't work out so well. Let's some magical gold nugget pile. Yay. Oh, that doesn't, maybe this isn't so great of a gold color. Let's try this one. Yes, much better. Gold nugget. So now we've got this pile of gold, and that's even better. Now we're motivated to solve this problem. Or maybe if that doesn't do it for you, perhaps it's a pile of mustard. Yes, delicious Hamilton produced mustard seed. Okay, so we have some this pile of mustard seed, and we want to know how much it weighs. So we calibrate this scale, and we've set it up so depending on where we lock this mass into position, we are going to be determining exactly what this has a weight of. So if we know how to analyze this thing, then you can design a scale, right? You can make it so this weight will balance out the torque produced through this complicated system by this weight but only if it's at the right spot. If you move this further out, it'll make more torque and overbalance. This thing will push down. If you move it about this more this way, then this one will outweigh it and it will not produce enough torque to counteract it anymore. So that's how you analyze machines. Exactly the same as with frames, but now often with one variable, as things can move and transmit forces through the structure. So here we're getting what's called mechanical advantage by leveraging, literally leveraging the fact that this produces a torque caused by its force times its distance, and messing around with what distance the forces are applied at, we have a force magnification as we move across from this small force over, making this have to be a lot larger since it's much closer to the moment arm that we're fixing, and then making this one have to be much larger since again it's much closer to the moment arm, and then making this one have to be much larger since it's closer to the moment arm again. Often a load isn't applied at a single point, but instead is distributed across a surface or along a surface. For example, hydrostatic pressure on the wall of a dam is a distributed load along that wall. That's what a distributed load is. So it means a force that isn't at just one spot, but is distributed. So we don't say the total force with this usually. We give the amount of force per unit length, because we're still doing 2D problems. So this is actually, in reality, a 3D thing, and we've got a pressure, which is a force per area. But if we kind of say the depth in and out of the page is a fixed amount and you multiply by that already, then we're going to turn that force per area into force per length at any spot. W is dependent on Y here, and it's going to have units of force per length. Okay, so W at Y, this means W is a function of Y and doesn't mean W times Y in this instance. So if this is the distributed force per length of the wall, then the force it produces on a segment dy at location y would be df, is the multiple of this. This is force per length, so you multiply by the length dy, and you get the force. Okay, so df is w at y times dy. The total force then would, I mean, not surprising, I think you know where this is going. We're going to integrate it to get the total force. So the total force would be the integral over the whole wall from y bottom to y top of w at y dy. The torque it creates, think about this for a moment. The torque df creates about a point y naught, would be the moment arm y minus y naught times df. Out of the page if y is above y naught, and it'll end up being into the page, or negative, if y is below y naught, if we were finding it about this point. Yeah. So the torque is y minus y naught times df, and if we integrate and substitute in the df that we said, then we have that the total torque would be this y minus y naught times the distributed load times the little bit of height of this wall, dy, to turn this into a force. So you integrate that and you get the total torque that this distributed load produces about that point y naught. And remember, this works whether the variable y is above or below y naught. It kind of fixes the direction there. So this is great. This is how you deal with distributed loads. We'll explore it with a few examples. Okay, first one, distributed load and piecewise functions. We've got this thing, and we're going to figure out what the reactions need to be in the support. So this is a roller support, which can move left and right. It can't apply a force in the x direction. And this is a pin support. It can supply a force in the x or y direction. And we have this distributed load here. Now, this is a way to say that we have a fixed distributed load of 6 kilonewtons per meter over here, and then it goes down to 0 linearly between B and C, but has a different slope over here between A and B when it rises up to a maximum of 4.8 kilonewtons per meter, and we've got the distances along the bottom here. So so this is what we're going to call W. This distributed load here is W. It's always in the down direction, but maybe we'll define W as a positive thing. Now, once we can write out W, then what we can say is that the net the net torque that's produced by W, let's just jump ahead a little bit. The net torque that's produced by W is going to be a little bit of torque times the position x that we're at. Let's set x equals 0 there. And then we're going to be multiplying by the force down. So just as a check, if a little bit of force here is creating W dx as the a little bit of width, I should say, is creating W dx, because W is the force per unit length. And so the dF, again, would be W dx. So we've got the distance out x times W dx is the force down. And then you can use the right-hand rule to find out that that creates a torque into the page about point B. Whereas the point over here, same right-hand rule, would create a torque out of the page about point B. But conveniently, again, it corrects for the x position that we're at. So over here, x is going to be negative. So if we just say that the torque is x times negative W dx, which is the downward little bit of force created over length dx by the distributed load W, then we're going to have it. So what we need to do is say that the net force is equal to 0 and the net torque is equal to 0. And we'll say the net force would be what? So the total force in the y direction is equal to 0, but that would be equal to by plus cy plus the integral of w. Oh, wait, but w we said is down, right? So integral of negative w dx from x is negative 0.9 meters to the right-hand side, which is 2.4 meters. Yeah, so that would be the total force, and this gives us one equation. And the other equation would be the total torque. Total torque at B is equal to 0, and that would be, let's see, we got a positive torque created by Cy. Cy times 1.8 meters. We'll put that in brackets to put it in front there. Okay, 1.8 meters times Cy. Yeah, plus the integral of d tau. So plus integral of x times negative w dx from x is, again, negative 0.9 meters to 2.4 meters. So just as a check, notice that we have the force from integrating the distributed load over the whole thing. It's always in the downward direction. We're going to define W as something that's positive everywhere. It's like 6 kilonewtons per meter over here, but it's directed down, and that's why we're adding negative W up over this thing to find the net force, because it's in the negative y direction. Right. And same thing for torque. We have x. If it was in the positive y direction, we'd be crossing x and a positive thing and get something that's positive out of the page, but it's x and a negative thing, so we get something that rotates this way and creates a torque into the page. Okay, so here we go. If we could somehow write what W was, then this would be it. We would have the net force and net torque is equal to 0, allowing us to solve for Cy with the torque equation and for By with the force equation. So all we need to do is figure out how to take this picture and then write this distributed load function, and ideally write it in Maple so that we can do this integral as easily as possible, and it's not going to get more difficult if W is more complicated. Okay, the first thing to do is to explore piecewise functions in Maple. So let's just make a W. W is going to map x to a piecewise function, and here's how it works. First, you get this is like an if statement. If x is greater than 2, then 3. If x is greater than 0, then 1. If x is less than 0, then negative 2. Sure. So here's going to be our x, and it writes it like that. Yeah. And then what we can do is plot it. Plot w, x is equal to negative 2 to 3. Sure. Whoops. It got messed up. What happened here? Plot w at x. There we go. Okay. Now, let's analyze what's going on here. So first, when you substitute into the piecewise function, it says, okay, w at, it's going to sub in a bunch of different x values. It puts in negative 2. And then how this works, and this is very important, it goes left to right, right? It doesn't read the later conditions first. So first it's going to look in and say, okay, is negative 2 greater than 2? No. So skip this condition. Is it greater than 0? No. So skip this condition. Is it less than 0? Yes. So we've got a negative 2. If it didn't find anything, if this was like less than, let's say negative 4, then in this situation it was said no answer and just return 0. Right, so the default for piecewise is still just a 0 there. It will evaluate to something. The other thing is if you take this same function and you write it in a different order, we're going to have a different result. Let's suppose first you go x is greater than 0, then a 1, and x is greater than 2, then a 3. It's never going to be 3, right? Why is that? Well, because when it substitutes in these values here, it says, okay, well, if x is greater than, let's suppose x is like 2.5, something that would have given 3 the way we wrote this earlier. When we substitute in 2.5, it hits the first condition, x is greater than 0, 1, okay, we're done. It doesn't bother to check this next one. This can never evaluate. It'll never be 3 as the output of this, because for x to be greater than 2 and this to be true, it would have already been greater than 0, so we would have hit the first condition and left the function. All right, so let's look at this a different way. You don't actually have to use function notation for this. We could just say w is equal to piecewise, and in fact it kind of likes to lay this out a little bit better rather than using this mapping notation. So you might just stick with this rather than doing the more complicated w maps x to this thing. Now w is just going to replace it with this piecewise function that involves x every time. Works totally fine. Yeah, okay, so in this particular case, what do we need for w? We need to make it a piecewise function, which if x is less than 0, let's start off with that condition, x is less than 0, then we've got this thing, something that's rising up to a height of 4.8 kilonewtons over a distance of 0.9. So 4.8 E3 over 0.9 is going to be the slope, but this is increasing as x gets more negative. So we're going to have negative x times that. Okay, so look at that. It's going up in that direction. And what do we want to plot it from? Plot from negative 0.9 to 2.4. That's the range we're looking at this from. So that doesn't quite, I mean, that looks pretty good. It rises up to a height of 4,800 newtons per meter. Once we get x is 0.9, I mean, you can also check that would work when you substitute it in. So this is a linear function that has the right slope and the right intercept of 0 at our x equals 0 point. So it works. That's it. Next one. If x is greater than 0, but we want x to be less than 1.8 and this function to stop then. So we'll say x is less than 1.8. And then we want x times, so we're going to be rising up to the right, and this slope. So that'd be the rise. It goes up to 6e3 over 1.8. Okay, so there we go. And then what we want after that is if x is greater than 1.8, then 6e3. Now there's no condition if x is equal to 1.8, but that's not important because we're just going to integrate this anyway. So I guess technically if you were to put in x is equal exactly to 1.8, then it'll evaluate to a 0 for a moment, but you can't see that in the plot. We're not going to hit that point. Okay, so there we go. There's our w. So then what we can do, I mean, besides plotting it and checking that it works okay, is write this force equation. So what we're going to do is solve, as usual, that by plus cy plus the integral of negative w times, well, w with respect to x. X is negative 0.9 to 2.4. This will give us the total force, right? Total force created by w. And we're also going to find the total torque created by the distributed load and cy about point B. And that'll be 1.8 times cy plus the integral of x times negative w from x is negative 0.9 to 2.4. Okay, let's see. So we've got cy is 7080 and by is 4080. Well, they're both positive, which kind of makes sense because we're fighting against a downward force there. And the moment created about B by this side is sort of stronger than the moment created about C by this side because of that drop to 0 before rising back up. So to counteract this large block of area that we'd have under the function here, this large integral, we need a larger force at C. So C needs to be larger than what's going on at B. These are both on the same order as what's happening with the height, because the distance is around 1-ish meters. So let's see, we've got, it's on the order of 1 is what I mean. So we have about 6,000. What's the average height? With this drop down and back up, we've got, actually we can figure that out. So what would the average height be? It would be the integral of W from x is negative 0.9 to 2.4, and then divide by 2.4 minus negative 0.9, right? Divide by the total length. So the average height is 3381, and the distance is this, right? So if we take this average and multiply by this distance, then we're going to get the total force. I guess we could have just integrated to find that, right? So let's take this. Yeah, so 160, and that's going to be the same as adding those two up. That makes sense. And yeah, I guess as another check, we could find the torque about point C. So see if you can write out what that would be. That should be, well, I'm not going to, yeah, okay, why not? Let's copy this. So after we've done this solve, we can assign it. And then here, we'll take torque about point C would be negative 1.8 times by. Then again, plus the integral of x times negative w from x is negative 0.9 to 2.4, except now the moment arm is not x anymore, it's x minus 1.8. So this should evaluate to 0 if we also now have no net torque about point C. Let's check. Yes, 0. 0.1 e minus 5. Compared to the size of these things, that's 0. So we did it. Anyway, that's how you deal with distributed loads. They create a force per unit length, and so after you multiply them by a little bit of length, dx, then you can find out the total force, and then just add up torques that they produce by multiplying by a moment arm like normal, and the facilities and the things that we built up to deal with problems in 2D have made this a lot easier to handle than if we didn't have those 2D problem-solving strategies. All right, so here's another problem with distributed loads. These are parabolas this time, and this makes it a fair bit more complicated. We have one parabola that starts they both hit 0 at this point when x is 4. Let's say that x is 4 there, and we'll set x equals 0 over there. This one goes up to 2 kilonewtons per meter on the left, and this one goes up to 1 kilonewton per meter over this distance. So they're actually not the same parabola, right? Because if it goes up to 1 over a span of 2, then as a parabola it should go up to 4 over a span of double 2. But this one goes up to 2 over that distance, so it's not the same parabola. Okay, so again, what we're going to do is, assign a let's just do a new solution here. So we're going to draw a free body diagram. And, well, it's not quite a free body diagram, I guess, because we kept the side in there. Let's make it a proper free body diagram, sure. All right, there we go. Get that, and now we can draw some reaction forces and moments. We'll say we've got like an AX over there. And we've got an AY. And let's set that as up. Sure. AY. And we've got a moment. And we can tell that the moment is going to be in this direction, because that's what the wall is going to have to do to stop this from falling down. MA. Okay, there we go. So there's our free body diagram. Yeah. Okay, so first start off with an FBD, and then what we're going to do is say that the net force in X is equal to 0, which equals AX. Not much interesting going on there. The net force in Y is equal to 0 as well, which is going to be AY minus, or maybe plus, the integral of negative w. I was going to say minus the integral of w, but let's just say the integral of negative plus the integral of negative w with respect to x from x is 0 to 6 meters. We've set x equals 0 at the left side when we're doing this. Okay. Why is this the case? Because the little bit of force created by a bit of distributed load dx is, or a bit of beam length dx, is w dx in the down direction. So we're going to integrate that to get the total force. What about the torque? Same idea. So the net torque at x equals 0, that'll be the easiest spot, is equal to 0. And this is, well, there's no torque created by AY, but there is a moment at MA. What else? Plus the distributed torque, which again, because W is pointed down, is x times negative W dx, integrated from x is equal to 0 to 6 meters over the whole length of the beam again. Okay, so, well, that's all well and good. That's all the physics that's there. There is a bit of math to do, which is to figure out what the distributed loads are. And so the distributed loads are parabolas, and we know that the form of a parabola is something times x squared, but that would be if it starts at x equals 0, right? So if instead it starts at x equals 4, then we have to shift it by 4 meters, right? We can say that the parabola then will have the form of something times x minus 4 squared. This is the parabola that starts at, well, that has a 0, that reaches a value of 0 when x is equal to 4. Okay, so they're both going to have the form of something times x minus 4 meters squared. X minus 4 meters all squared, the square outside of the brackets. And then we just need to find out what that something is. So we can do that by using the other points that we know. When x is equal to 0, then we need this first parabola to give us a value for A, for the thing in front, so that we get overall 2 kilonewtons per meter. And we can kind of do that in Maple. Why not? So we'll say solve W1. Okay, how about this? Let's say W1 is equal to A times x minus 4 all squared. And W2 is equal to B times x minus 4 all squared. Then what we'll say is we'll solve subs x equals 0 into W1. And what should this be? When we substitute x is 0 into W1, we should get 2 kilonewtons per meter. Right? So that tells you what A is. So A is going to be that. We can do both at once, right? We can say subs x equals 0 into W1 should give us 2E3, and substitute x equals 6 into W2 should give us 1E3. All right, and that solves for what A and B are, so let's assign that. And now we've got our W's. Now the overall W would be if x is less than 4, then W1, x is greater than 4, W2. So now we can plot that. Plot W, x equals 0 to 6, and check that it worked. All right, that looks pretty good. It goes up to 2 kilonewtons per meter when x is 0. And as we go over to x equals 6, it goes up to 1 kilonewton per meter. And look at this. You can really see in this picture how much steeper the parabola is on the right. Yeah? Yeah. I wonder if we can get it to look a little bit like that one there. Yeah, that looks okay, eh? Pretty good. Okay, so there's our W reproduced. What else can we do? Hey, if we re-execute this, will it resize it? No, nice, keeps it. Okay, that's pretty cool. Oh yeah, we were solving a statics problem. So what we'll do is we'll say now solve AX, sure, let's put it in, AY plus integral of negative W, x equals 0 to 6, and the last one, the torque equation, is MA plus the integral of x times negative W from x is 0 to 6 again. Okay, so we've got that AY is a little bit more than 3K. It's like a 6-meter long beam, and it rises up to at most 2, but most of the time it's a lot less than that, like 1-ish, less than, I guess even half that. So that makes sense that it's more like 3K instead of like 6K. And MA is 6K because then the length has, let's think about that. Why would that be the case? Because we've got an average of 3,300, and if that, how far out is it on average? Maybe a little bit closer than halfway, right? 2-ish. So 2 times that would give us, sure, okay. Yeah, and that actually brings us to the next topic. So the moment being 6K makes sense because we've got forces that are about, that has an average of 3K, but it's on average not very far away, right? So we can take only at most like 2K far away on average for this thing. And that is what is responsible for giving us this moment. So the next topic points out, you know, you could replace this whole thing with one point force, and that has the same effect as this whole parabola, and put that point force at a location so that it creates the same moment. And this is kind of a weird concept, right? It's a little bit strange for how to do it. It might not seem like there's a point. And there isn't much of a point for this parabola one, but for something like a triangle shape or this flat line, it becomes a fair bit more useful. For example, have a look at this situation. It's going to turn out that you can take this distributed load here and replace it with a single point force in the middle, and this one, and replace it with a single point force that's 2/3 of the way to the right. How much force do you need for that? Well, you need one that definitely is going to produce the same net force as these things, yeah? And this has the same net force in the y direction, this distributed load, as a single 300 Newton force. Why? Because if you integrate this, it goes up to 200, and it starts at 0, so on average it's 100, and we've got a distance of 3, so 100 newtons per meter times 3 meters is 300 newtons. This one, 100 newtons per meter times 6 meters, 600 newtons. Yeah, so if this is equivalent to any single force, it's got to be equivalent to a 300 Newton one in the y direction, and this has to be equivalent to a 600 Newton one in the negative x direction. Well, negative y for this one up top too. Okay, now, where do we put it? Let's look at this one first. How do we know that it's supposed to be in the middle? Well, what we would need is that the torque created about point C, or let's say, the torque from the 600 Newton force at point C is equal to the integral of the little bit of force from that thing times y, right? Overall of y from, let's say, C to B. Now, what is the force that's created? Well, it is y times w, which is 100 newtons per meter. Oh, wait a minute. Sorry. The force is just 100 newtons per meter distributed load times dy. Okay. That would be what we get when we integrate this over that whole range. We're just integrating 100 newtons per meter dy over that whole thing. Now, the idea is, if there is some equivalent, well, wait, let's check the direction. Y up, and then 100 newtons dy to the left. Yep. Okay, so that'll be that cross the force will give us a torque out of the page. Okay, now if there is a force that we could put somewhere, then it has to be, so it has to have the same net torque and net force. So So what does that mean? Well, the net force, we already figured out it has to be 600 newtons. We could write an equivalent equation for that. We're going to say that the force from the 600 newtons would be equal to the integral of just this W, right? Times, well, over the whole thing, right? From 0 to 6 meters, from C to B. And that has to be the same as the equivalent one. So we figured out that the equivalent one is equal to 600 newtons. 6 meters times 100 newtons per meter will give us 600 newtons. Okay, now where is Y equivalent? Well, what we have here is, look at this. This is kind of interesting, right? This is Y equiv is equal to, what's this? It is going to be the integral that we use to find the torque, which is Y times the distributed load W dy over the equivalent force. But the equivalent force was just this same integral without that Y. You might have seen something like this before. This is an average Y, right? This is the average Y location of this whole thing, because we're integrating over the whole beam. W, which is just a constant, so you can take that out, it cancels. Y over just the integral of that whole thing. So this is the average Y, right? You might call this like Y bar on this beam. So the equivalent location for this distributed load to be, for the equivalent force to this distributed load, to then produce the same torque about any point, or at least when we calculated it about C, is the average Y. It turns out that'll be the same no matter which point we found it about. So if we were finding the torque about some different point, then how would that have worked? Torque about a different point, we would have just had, let's say Y minus Y naught, right? And that would have been here, minus Y naught, and over here, it would be at the equivalent spot, right? So guess what? We get our Y naught coming out of this integral, and then we have the same thing over here. There's now, which is, yeah, let me just show you that in case that's not jumping out at you. But we have that one, and over here, this thing times equivalent. Okay, so we'll get a split of this integral over two different terms, right? This and then Y naught. But look at that. This integral, the Y naught can come out of it because it's just a constant. And this is the same integral we had for F equiv. So the Y naught F equivs are going to cancel, and then we're left with the exact same thing as before. We're left with saying that no matter what point we were finding the torque about, this is Y equiv times F equiv. So the equivalent Y that is going to be where you locate this thing to produce the same net torque is just in the average Y position. Okay, now we left W in there in a bunch of different terms, but what if W wasn't a constant function, right? What if instead W was not a constant? What if we had a variable W? Well, nothing about this would have really changed. We just have this thing that is 100 newtons per meter would just be our variable W, right? So then what we're always going to end up with is kind of a weighted average position where the weight that we're using is the distributed load. So we're going to be finding the average position, weighting it by this constant, that's just the average position. But up here, we'll find the average position where we weight it. We give more power to the average where the distributed load is more, and that's what shifts it to the right by this amount. We can try that out in Maple and see where this is. And we're always going to get 2/3 over to the right. So let's take this for a try. A is 0, B is 1, sure, and W is equal to some triangle function. So let's say 200 newtons per meter, okay, over 3 meters. Sure. Now this is not actually the same distance. B is actually supposed to be 3 here, but it turns out it's not quite going to matter. So yes. Now what we'll do is we'll say that x bar, the x location or x equiv, let's call it, is equal to the integral of x times w from x's a to b, and then divide by the integral of w from x's a to b. This is a weighted average of x, where the weight function is, in this case, the distributed load. So we get 9 over 2b. What did I do? I typed in the wrong b. Okay, a to b. So we have x equivalent is 3 over 2. Okay, what's 3 over 2 compared to a and b? That's right in the middle, right? So yes, why didn't it show up at 2/3? Because we did w as a constant. We didn't actually make it linear, right? W is a constant at the top and the equivalent one is right in the middle. That's just reproducing this result. But if now we make this times x, the equivalent spot is 2. Aha! The weighted average getting the of this thing now with as the weight function has shifted the equivalent spot to put this thing over more to the right. So then if this is the case, it means that what we can do is we can say that the torque produced by, first of all, F equiv is the integral of W from x's a to b, and the torque at A would be equal to the, let's say the torque at A produced by this thing would be equal to, let's get this Microsoft search thing there, would be the integral of x times negative W from x's A to B. That's the raw torque. Now what about the torque produced by the equivalent load? Well, if we just take x equiv, where we're saying we ought to put this equivalent load to get the same torque, times F equiv, then we get the same size thing. I mean, we didn't use the right-hand rule that time very well. Negative F equiv. And there we go. So torque at A is equal to negative 600 by doing the raw integral of x times the distributed load from A to B. But instead of doing that integral, if you like, you can just say, hey, you know what? This is a linear function. I know the equivalent spot is 2/3 of the way, and therefore the torque that it should produce is what is the equivalent force multiplied by 2/3 of the distance. Now this sounds nuts when we're using Maple. Like, why think about these equivalent forces? It was a very big deal before people had very powerful computer algebra systems. And so you would just have a table of a bunch of shapes of distributed load you might have and like where their equivalent force would be so that you can find the torque quite easily rather than having to do these integrals. But now you can just set up the computer algebra system to find the integral for you, and you don't have to worry about finding these equivalent spots. But it does help with your sense checks. It is helpful for thinking, okay, well, wait a minute. What was the torque that this should produce? Now that you think about this and you think, okay, well, triangle, the weighted average of this position is 2/3 of the way. This should create a torque that's just like a 2 meter times 300 Newton per meter. So should produce 600 Newton meters of torque in that direction about A. This one, 600 Newtons, and it is 3 down. So we got 600 from that, and we've got 6 times 3 is 1800. So we should have in total 2400 Newton meters of torque about A if point C was not there. Right. So you can do those sorts of quick thinking it through checks to see if your computer calculations have worked, because remember, I can say it again and again, even though the computer has so many digits of precision, doesn't mean it's always right. Thanks for watching. I'll see you next time.